Let's have a look on the problem 2080 from lead code, range frequency queries. This is the problem description or the problem statement. It asks design a data structure to find the frequency of a given value in a given subarray. The frequency of a value in a subarray is the number of occurrences of that value in the subarray. Implement the range freq query class. This class already implemented here because the course resolved this soon. Initially, we have only these two functions in this class. Of course, we don't have any attributes. The function range freq query, it takes as parameter an array that will construct an instance of the class with the given 0 indexed integer array. This function will construct the data structure that we will use to resolve the problem. The function query, it will take as parameter three parameters, left, right, and value. All of them are integers, and it will return the number or the frequency of this value in this subarray from left to right. Let's take an example here. The input is like this in this problem. First, we will call the function range freq query to construct your data structure, and then we will give you a number of queries. This is the elements, and this is the queries. We have two queries here. On this first query, for example, from 1 to 2, how many 4? From 1 to 2. From 1 to 2 is 1, 2, we have just 1 4. And from 0 to 11, how many? 33. 0 to 11, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 on all the array. How many 33? We have 2, as you see. So the answer or the output will be null because this is the call of the construction. And the queries only, I will have two queries. The output will be 1 for 4 and 2 for 33. Let's understand more the problem. If I have this array and I have a query 4, 9, 4, which means how many 4? This one, this 4. How many 4? From 4 to 9. As you see in the slide here, how many 4s? From 4 to 9. We have only 2 4s. From 0 to 4, how many 6? 2. From 0 to 4, how many 12? Just 1. From 10 to 19, how many 6? This one, and this one. And so we have 3 6s. We can use the naive approach to resolve this problem, which means for each query left-right value, and for each element AI of the subarray where I is from left to right, we check if that element AI is equal to this value. So we increment the answer by 1. Of course, at the beginning, the answer is equal to 0. The type complexity of this query function is q times n, where q is the number of query and n is the size of the array. If we implement this solution, as you see in the picture here, we will get a time limit exceeded, a TLE. As you see here, the range of frequency, we will build a new array that will take the elements of the original array, because in this function we can't use this array. We can't use this array here because we can't access to the instance of this class in the program. Just the code gives us only these two functions to implement. So my solution in the range query, I will build a new array. I will give it as attribute here, and this array, I will use this array to use this naive approach. As you see, I iterate from left to right, and every time the element AI is equal to value, I increment the answer, and I finally return the answer. This approach gives me time limit exceeded, because its time complexity is big O Q times N. And the space complexity is an extra step. We have an extra space complexity is the big O N, and the whole or overall time complexity is 2 O big O N. We can use another approach, which is preprocess all answers, which means I will compute the frequency of all the elements in this array. I will build a hash map for the guys who do Java, or a map, or an ordered map for the guys with C++, or the dictionary for the guys with Python. And I will build a matrix of size. As you see, of size 6 times 5, which means of size n plus 1 times n. Initially, I will initialize all the matrix by this map, and I will compute when I am at the first element, which means how many. In this case, how many 6 from 0 to 0? So I have just 1 6 and 2 0 and 0 2s, sorry, and we have no 4. From 0 to 1. Now, how many? What I have here from 0 to 1? I have 1 6, 1 2, and 0 4. From 0 to 2 in the original array, I have 1 6. Now I have 2 2s. As you see, 2 is identity here. The frequency of 2, this is the frequency, this is the element. The frequency of 2 is updated. From 0 to 3, I have 2 6s, 2 2s, and 0 4. From 0 to 4, I have 2 6s, 2 2s, and 1 4. From 0 to 5, I have 2 6s, 3 2s, and 1 4. And now I will pre-compute from 1, which means from 1 to 1 now I have, yes, I have 0, 6, just 1, 2, and 0, 4. From 1 to 2 I have 2 2's, 0, 6, and 0, 4, and so on for the rest of the row. Now from 2, which means from 2 to 2 I have just 1 2, 0, 6, and 0, 4. From 2 to 2. From 2 to 4 I have 1 6, 1 2, or from 2 to 3, sorry, I have 1 6, 1 2, 0, 4. From 2 to 4 I have 1 6, 1 2, 1 4. From 2 to 5 I have 1 6, 2 2's, and 1 4. Now from 3 to 3 I have just 1 6, 0 2, and 0 4, and so on. From 4 to 4 I have just 1 4, 0 6, 0 2. And from 4 to 5 I have 1 2, 1 4, 0 6. And from 5 I have, from 5 to 5 I have just 1 2, 0 6, and 0 4. As you see here, I'll pre-compute all the answers for all this subarray. How we will the pseudocode of this? First, I will declare a matrix or a 2D array of size n times n plus 1. Initialize n to this frequency, to this map, and I will compute. Then I will compute all the answers like this. I will iterate first on the rows from 0 to n, and for each row I will iterate for all the columns from I plus 1 until n plus 1. I think here it's wrong here. It's not included, this one, and this one is not included. Okay, first Mij, which means a cell. Let's take this cell Aj. First, it will take the values or the dictionary or the map of the previous cell. Then it will be updated. The value of the given value, it will be updated by this instruction. Okay, let's take this one for example. Here, first it will take the previous map, alternate map, this one, which means 60214440, this instruction. Then from 2, here we are from 2 to 3. From 2 to 3, because we have 4 here. From 2 to 3. First, from 2 to 3, we have here this dictionary or this map. It will take like this. Let's write it here. 602140. Of the value 6, it will be incremented by 1, which means this one, the 6 here. The next one, if we are here now, if we are here, so it will be 6121. It will It will take the previous an object map for the and the next instruction here, this map we will update this one 4 is incremented by 1. It will be here 1, as you see here, from 0 to 1. The time complexity, it will be big. The pre-processing time complexity, it will be big O n squared quadratic, and space complexity we have 2n cube. Why 2n cube? Because we have n squared. We have n square elements, we have n square size of the matrix, and for each matrix we have plus, not plus here, multiplied by 1. In the worst case, it will multiply by 2n. Why 2n? Because for each element, we have another integer, which is the frequency. So we have the first. In the worst case, if we have all the elements, all of them 1, 1, 1, 1. In the worst case, we will have all the elements in the dictionary, and for each element, we will have its frequency. So we have 2 times, so it will be 2n cubed, the space complexity. If we implement this, as you see here, first I declare a new type, it's an ordered map. This is the element, it's a frequency. I will put the matrix as a public attribute of the class. Now the function range of query, we will construct our preprocessing to the array. First, we will count, we will build the an ordered map. All the frequency is equal to 0 for now. Then, for each cell of the matrix, we will push. We will for each row we will push that an ordered map, as you see here. Then we will push that row on the to build the columns. Now this is we initialize the matrix to that dictionary or to that unordered map. Initialize all the elements are initialized to 0. Then we will update all the elements in the matrix, as we have seen in the previous slide. This will take O n squared time complexity. For the query now, it's easy to see it. We have, if you want a query, we have all the preprocessed answers. If we have, for example, to how many 2 from 1 to 3, just came here from 1. This is row 1, and column 4. Why 4? Because don't forget we add a column here on the array to the array size. So we get this cell. How many 2 we have here? We have 2. So we will write this instruction: m of left and right plus 1 of value will access the frequency of a value in the cell. This is O1, constant time. But the problem here on the processing, that's why we have a time limit exceeded. We can use the technique square root decomposition, as we have seen in this lecture at the beginning. If guys you forget how to build or how to use this technique, just come back to the video where I explain in details all this stuff about the square root decomposition. Now the time complexity is big O square of n, where n is the size of the big original array. Let's first build this array of blocks. We're going to divide the original array into blocks of size square root of n. Here we choose the ceiling is equal to 5. And for each block, we will compute the frequency of its elements. For example, here for the first block, this one, we have 2 6s, 1 12, 1 2, and 1 4. For the next one, we have 1 11, 1 12, 1 4, 1 10, 1 25. For this block, we have 2 6s, 1 100, etc. And this block, we have this computation. This is how to build the array of blocks in the square root decomposition. How to query now? It's quite easy. We have seen this in the lecture. For example, from 3 to 17. From 3 to 17, we start from 3. We ask ourselves, is the 3 is the beginning of a block? The answer is no here. So we check is at 3 is we have 6 here. Therefore, the answer is yes. So we add 1 to the answer. We go to the next element. Is index 4 at 4 here? Is the beginning of is it the beginning of a block? The answer is no. We check at 4. We have 4 is not 6. So we do nothing here. We just go to the next element. At 5. Here 5 is the beginning of a block. So we can go directly to this block and check how many 6 we have. We have just 0 6. We have no 6s here. So we do nothing. We jump to the next block. Because of this block we have no 6. 10 is the beginning of a block. So we check on that block how many 6. We have 2 6s as you see here. So we update the answer. 1 plus 2 is equal to 3. And we jump to the next block. 15 is also the beginning of the block, but we have to be careful here because we don't look to the entire block here. We stop at 17. So, which means if we have a 6, for example, here, it will not be in the answer. Which means we have to go element by element in this case. Check 15. We have in 15 we have 6, so we add 1. We go to the next element. To 16 we have 6, we add 1. We go to 17, to the right position, to the right boundary. We have 10, so we do nothing. So we have from 3 to 17, we have 5, 6. If we implement this, as you see, the answer is accepted. The solution is accepted because The single query time complexity is big O square root of n, and the overall all time complexity is On, which is the pre-processing time complexity to build the array of blocks, plus the complexity of all the queries, which is q times big square root of n. Q is the number of queries, which is, so we can say the time complexity is big O q times square root of n. The overall space complexity is, we can say, big O to n. So, in the function range of Freike query, we have to build our array of blocks. We have to compute the size of the array of blocks. And we build it as you see here in this form. We have seen this in details in this lecture. We can come back to the video and see it. And the query, as you see, while left isn't, we don't have reached the right boundary. We check every time if we are at the beginning of a block, and is that block the current block? We have to check the entire block. If these two conditions is okay, we can just use the answer in that block and jump to the next block. If not, we have to check element by element, as we have seen in this previous slide. Can we use a sparse table here? The answer is no. The sparse table we can't use here because we have to, in this situation, we have to compute the sum of each element. The sum of each element, as we have seen in this lecture. To use the sparse table, the function it must be an idempotent function, which means if the function is f, which means f(x) of x, it will be equal to x. If the function is minimum, for example, the minimum of x and x is equal to x. We can use the sparse table here. But for the sum, is the sum x and x is equal to x? No. The sum x and x is equal to 2x. If we are not convinced, we can try to use it and see what happened here. Of course, to build the sparse table, you know how to build it normally, because we have seen this in details in this lecture. We have to compute the size of this 2D array. It will be if my array is from 0 to 19, it will be from 0 to 19 in the rows, and we have here 5 on the columns because we have to take the floor of the size plus 1. And each time we will compute the frequency of each element. For example, here in the first column we have just 1, 6, 1, 12, 1, 2, 1, 6, 1, 4. We take all the element by itself, each element by itself. In the next element we have to take or to merge this one and this one to get this one. And for the second, for example, we have to take this one and this one to take this one, etc. Here, for example, to take this, to get this, we have to merge this, and I think this one. No, let me not do that. To get this, we have to merge this and this, yes, and this one. To get this one, I have to merge this and this. Where is it? This one. You can ask, how do you know that? We have explained this, guys. It's a waste of time to repeat all the stuff in this problem. Okay, let's see a query now. How to query? To query, for example, I want to know how many 100 from 3 to 70. So first I have to compute the length of this subarray, which means 17. I think I have this example here. Okay, from 3 to 16, how many 6, for example? First I have to compute the length, which is 15 elements here. The length is 15. We compute K, which is the floor of log base 2 of 15. And we compute an P, which is right plus 1 minus 2 times 3, minus 2 power 3 is equal to 10. So here we have to look at the element at the 3, 3, which is this one, 3, 3, this one, and 10, 3, this one. Which one we will to take? From 3 to 16, how many 6 we have here in the original array? We have, I think, 1, 2, 3, 4. We have 4 6. Okay. You may tell me why not we can merge these two results. Okay, because we have 6 1 here and 6 3 here. So 3 plus 1, we have 4 6. Then we have the correct answer. But if I tell you, give me the answer of 100. Right? If we continue with the same logic, we have to merge. If we merge this, we have 101 here and 101 here. If we merge, we have 102. So we have, but we don't have 200 here. We have just 100. So the answer is wrong. That's why we can't use the sparse table here. In general, if I have my original array, I can get the first interval or the first subarray from here to here. I have, for example, x element for a value v. We have x here, and I can get another array from here to here. It could be we have another x here, another x here. So this one, it will count it 2 times. So the answer is 1 because we want the sum of them. So we can't use the sparse table in this case. What about the segment tree? If I have this original array, I can build the tree, the segment tree. We have seen the segment tree in this lecture. We go left and we divide by 2 each time. Yeah, and finally we can get a binary tree. As you see here, we have in the 3 3 we have just 1 6, and 4 4 we have 1 4. So from 3 to 4 we have 1 6 1 4. From 3 to 5 we can get, from 5 to 5 we have 1 2. So in this from 3 to 5 in this node, we have 1, 6, 1, 4, 1, 2. And from 0 to 2, we have 1, 6, 2, 2s. And we can merge them in the root. We have 6, 2, 2, 6, sorry, 1, 4, and 3 2s. So from 0 to 5, we have all this element. How to query now? To query, for example, let's take, I want to know how many 2 I have from 1 to 4. From 1 to 4, we check the root. 0, 5, the root is the interval of the root. We have a partial overlap. So we go left and right. Let's go left first. And then the node 1, we have the interval 0, 2. 1, 4, and 0, 2, we have a partial overlap. We go left and right. We go left first. 0, 1. 1, 4, and 0, 1, we have a total overlap. So we return this result, which means we have to check in the node, in the data of that node, which is the unordered map. Say we have 1, 6, 1, 2. With the value of 2 of that map is equal to 1. And we go right now because we have a partial overlap on the node 1, the interval 0, 2. Same here, we have total overlap. So we return the result. Sorry, here I have a mistake. We have here just. Okay. Here just that map to 1. How many 2 in that map? Just 1. And so, because I have returned from the right side the result, and from the left side we have another result, we can merge them or add them together. 1 plus 1 is equal to 2. Yes, which means from 0 to 2, we have 2 2s. Now we go right, because we have a partial overlap between 1, 4, and 0, 5. We go right. 3, 5, and 1, 4. 3, 5, and 1, 4, we have a partial overlap. We go left and right. We go left first. 1, 4, 3, 4. 1, 4, 3, 4, we have a total overlap. So we return that result. 6, 1, 4, 1 over value 2, we have 0 because we don't have 2 on that map. We go right now. 5, 5, 5, 5, and 1, 4. We have no overlap here, so we return 0. Just 0 like that. We can do the summation between these two results from the right side and the left side, which means 0 plus 0 is equal to 0. Now we have the both results from the left and from the right. We can add them together and we have the final result, which means from 1 to 4 we have only 2. We can implement this, of course, using an array for the segment tree. Here is my segment tree. This is the size of the arrays. How to build the segment tree? If we come back to the build animation here, as you see, when I have a leaf, the data and the leaf is known because it will contain just one element of the array, and that node we have only from 0 to 0 we have only 1, 6, and on that node from 1 to 1 we have only 1, 2. Now we can merge them and put the result on their parent, which is that node. So we merge both results of the two leaves. And now from 0 to 2, we have the 2, 2 first, and the element in the array 2, 2, we have just 1, 2. And now we have the elements here, this map, this node, and this map and this node. We can merge them and put the result in their parents. Same for the right side. We merge the data and put it in the parent. Same here, we merge the data of the two children, and then merge all the data from the left subarray and the right subarray and it. So here, to build this in the function range operator query, we build our segment tree. We compute the size. We compute the size of the segment tree, which is, as we have seen, m. The size is m is 2 times 2 power k minus 1, which k is the log base 2 of n. N is the size of the array. We call this function to build our segment tree using an array. We give, of course, the original array and the interval of the root from 0 to n minus 1, and the position of the root and the segment tree, which is position 0. Here, our function build. It will take as parameter the original array, the start position, the end position, and the position of the node. The node is the root, the first call. If we have a leaf, just update the map of that node by that value is equal to 1, and come back to the previous call. Otherwise, divide the array by 2, go left, and then go right. After going left and go right, if the two computations are done, we on that node at position P, which is the parent of these two left and right children, merge the two data which are the unordered map on the left side and the unordered map on the right side, and merge them together. This is the function merge. It's easy to use. As you see, it's not a big deal. The query, how to query in segment tree, you know this. If we have no overlap, return 0. If we have a total overlap, return that result. This is the map. This is the value in that map. What's the frequency? What's the frequency of P of that map? Otherwise, if we have a partial overlap, we go left, then we go right. Okay. As you see, this solution is accepted because the time complexity of the single query is log m, where m is the size of the segment tree, and the overall time complexity is the q times log n, and overall space complexity is O big O m plus O n, which is the size of the original array. Okay. But here, guys, I have to mention that, let's see the submissions here. If I use a segment tree using point, I have a memory limit exceeded. To be honest, I don't know why. Maybe because we have an extra data here, an extra information, which is the struct node. Speak especially about this both data, left node and right node, or maybe when I merge a function merge, no, there's no an extra memory here. Maybe all this, maybe I don't know. Please guys keep this in comments. I don't know why we have a memory limit exceeded. I use the same logic of the segment tree, but using pointers gives me a memory limit exceeded.